There it is.
There we go.
Yeah, the funds of tech.
I just never press join audio.
Well, it sucks.
It's
Like
fine.
we learned a lot about like graph theory, but I felt like this competition barely had any graph problems.
Yeah, I don't think it had much.
No. Honestly, the one where we went over like GCD had more problems.
Yeah, exactly. Yeah, that makes sense. Like I thought we were gonna have a competition full of like, all right, you got BFS and like DFS and whatever. Nope, not at all.
Although, let me actually check
Yeah.
because I'm pulling up it because I'm curious.
there
let's
there
just
might be
say
one.
You
I
can
don't
totally
think
do
so.
some of these the wrong way.
Yeah,
and use
exactly.
graphs.
Like sometimes like a problem doesn't directly use
one-
graphs, but
This one could kind of be a graph problem if you consider it to be a BFS.
Oh, that one.
Yeah,
mhm.
literacy.
Would the optimal solution be backtracking or something? I wouldn't know for this.
No, I think just BFS is
BFS actually?
the intended solution because
Really?
the number of states you have is limited. There's only 6 letters, and you have a string of 8 of them.
Mm-hmm.
So there's only like 6 to the 8 possible states, and you could just go through them. But yeah, you could. I mean, you could do it like DFS as well, but then like since you need the smallest number of steps, it's just way easier just to do BFS.
Okay, so BFS actually would just get this one down.
What's up, bro?
Yeah,
What's up,
it's
what's
like
up?
this one is like kind of annoying with all these different
Yeah, it's got so
rules
many
that you have to
conditions.
do.
So like BFS, you'd have to like go down each of those paths, essentially.
You have to consider like rotating on every single character, and then you would have to have like if statements to do every single rotation behavior.
Jeez. Wouldn't that be more like
Which
a
there's
brute
a lot.
force though? Wouldn't that be more like
it's not a brute force if you don't go back to any of the states that you've seen before.
Okay.
So do you have to do BFS and just mark visited?
Yeah, like when you do BFS, you have like your visited array. Yeah, it's like that. He said maybe you could do it with a string or something.
Yeah.
It's like a hash set of strings and do it.
And then one of the only ones that looked like a graph problem, rectangles, is totally not a graph problem.
Not.
Is it supposed to be a what is it, like point sweep with segment tree?
Yes.
Okay.
We'll get to that.
Someone was showing me kind of the approach in the lab, and good Lord have mercy.
Yeah, and there's no other graph problems.
You have to essentially, like, the trick is the general idea is you just use like a really long sweep.
I'll start talking about rectangles then, I guess.
Yeah, that's interesting. I think rectangles is the one that like it felt nice. Like it was like, oh, this is a interesting one. And then it's just like, okay, I'm lost.
Yeah, so
Ooh, Kyle, I'm gonna ask you about rugs or about rug later, I guess.
Goat rope?
I mean
rug.
I'll be going over rugs as well.
Okay.
But Coach Gabe, do you argue we should attempt to do problem reviews like varsity does?
Problem views?
Problem review. Like
whoever
how
solves
varsity
a problem, they explain the solution.
Oh, I guess we could do that maybe next time though, because
Oh, sure.
I wasn't prepared to.
No, I'm just wondering if
that
that's like
fun. Yeah.
Does it give, because I'm just wondering if it gives like benefits to us long term to do that.
Well, it probably helps the person who's explaining, because then you solidify it in your own head.
Probably. I don't know.
But yeah, that's like not a bad idea. could post that in the Discord channel. So like if you solve, I guess like if you get the dark green for the problem, you get to, well, is this an incentive or a disincentive for getting
Ooh, an
dark greens?
incentive? Oh boy, did you just figure out a
it depends
dark
on the
solution?
greens,
It
dark
depends
greens
on the
are
person
incentive
whether
on
they
their
want to
own.
do it or not, right?
I mean,
We
dark
do though if
greens,
someone who's not varsity gets a dark green or not junior varsity.
All right, I guess I'll give the person the option of whether they want to
That sounds
present for the problem or not.
all right. Just an idea for the future, I guess. Seems interesting.
All right, so
Rectangles.
moving on because we don't have that much time. Some of the bounds here. Well, actually, let's talk about what the problem is first, I guess, since I haven't actually done that. You're giving a bunch of rectangles, and they will overlap like this, where it's it's XOR, where like they'll cancel each other out. But if you had like an odd number of overlapping rectangles, then it's black. If it's an even number, it's like white. And then you want to count every single black pixel there is. And you can see right off the bat, there's like quite a few rectangles, 100,000 of them. So you can't do like many, like the n squared solutions that you may think of. And then also the bounds are large, 10 to the 9 here. So can't exactly make like a 2D array of this size. But there is like a trick here because there is only 100,000 rectangles. So what you can do is coordinate compress it. This is like a breakdown of one of the samples where they had like a rectangle. Actually, was it from like 1, 1 to 4, 4? I may have not represented this exactly right.
0, 0 to 4, 4, 1, 1 to 3, 3.
Oh no, maybe I think I did have it right then. Right. So I don't have the endpoints here, but yeah, maybe I can like write that down here. Like we had opposite corners at 0, 0, 4, 4. And then another one was 1, 1, 3, 3. If you look at that, you can see that like the coordinate 2 like doesn't show up for either X or Y. So when you're coordinate compressed, you can kind of imagine that you don't have to consider 2 because it would never show up on the boundary of a rectangle. And so you can kind of merge the cells together. Like in here, I've remapped them. So now it's 0, 1, 2, 3 instead of 0, 1, 2, 3, 4. And then the one cell is like actually representing the previous, like both the 1 and 2 together. And you can see that like, it changes like the size of some of the pixels here, but you can keep track of like how large your compressed coordinates are. And then you can use that to figure out like how large any given area is or any given pixel is. But there's still a problem with this because with the bounds here, this is a set here of 100,000, you still can't save, 100,000 by 100,000 or do anything with 100,000 by 100,000. So you still need to do something else on top of that to make this work. And that's going to be some kind of data structure. What I'm talking about here is a segment tree. I think range tree might be another data structure that isn't equivalent. That would also work. Yeah, I'm definitely most familiar with segment tree. So how do we use a data structure to kind of save space? And then Kyle is right that it was a sweep. So you can imagine sweeping. Let's just say we're going in X, but you could do it in Y as well. As you sweep through, you could add in like the columns of cells as they are like flipped or not. Or I guess you could flip the columns of bits as you go along from left to right based on the y-axis. So for example, you start at 0, you have like everything gets turned on because of the rectangle that starts at 0, 0. And then, you know, this one turns on the entire column. And then when you go to this coordinate, then the other rectangle comes in here and it flips these bits. And then now you have a sort of, you know, 4 of your bits here, you have these 2. And then if you go on, once you get to this one, you see that these have been flipped again. They come back. A nice thing about this like sweep idea are just like a small kind of convenience is that you don't have to distinguish between like whether you're starting or ending a rectangle, because in both cases, like you just flip it. Like here, you're flipping from off to on, and here you're flipping from on to off. But it really doesn't matter. Like you could have other rectangles in here, and these may have been black because of some other rectangle, but you're still doing the same operate. You're still just flipping whatever it is. And so when we're thinking about in the context of a sweep, what we want to do is we want to be able to flip like ranges of bits like quickly, instead of like, you know, having to do a loop of 100,000. And then we also want to like query like what are our bits that are on, like how many are there. And if we're swooping over X, it just so happens with this technique that you don't need to coordinate compress along the dimension that you're sweeping. It's just like because if you're counting the width of the column, you know like how wide it is. You don't have to necessarily consider every X coordinate because you're sweeping through the endpoints of rectangles.
Hey, coach.
Yeah.
Someone's been waiting to be let into the meeting apparently.
Maybe I need to change the settings. So under security.
Hey, Lana.
Ah.
Hi.
Hey, sorry about that.
That's cool.
I don't know where the setting is for that. So if anyone else sees that someone else is in the queue, go ahead and let me know. All right, I'm in the middle of explaining this rectangles problem, but it's not going to make much sense from the middle, so sorry about that. All right, but as I was saying, we want to be able to flip like ranges of bits, and we want to like also query, you know, how many are flipped. And this is something that we can do with a segment tree. And I've kind of made like a sort of a representation of a segment tree. In this case, like here, these, I just want to highlight this. These indices here, these could be the you know, compressed y coordinates and just like ID'd in increasing order. And you can see here that there's cells like, you know, at first, like at this level, there's like 1 for each, but then now there's like 2 for each, and then, you know, 4 for each. Like it, you know, just grows in powers of 2. If it's not a perfect power of 2, you can just, you know, like fill it out, like whatever the power of 2 that you would, you can just fit the largest power of 2 for the remaining space until you don't have space anymore. Like if there was, 3 more numbers here per se, and you're at like this level, then you could add like a block of size 2 and then a block of size 1. But yeah, but I'm just gonna leave this here as, you know, it's a perfect power of 2. I've added some numbers here, just because I think it helps to think about this problem in particular. These numbers here in the clear boxes are the sizes of, you know, each cell. So if you look at this, you can see that like for this y coordinate, you know, this one cell is like larger, like it is like size 2, like it's twice as big as the other ones here. And that's what's like being saved here, although I kind of have a more complicated example, but like this is like the same, like this is a cell size 2, size 3. And then as you go up the levels here, these are, by the way, these are nodes in the segment tree. And as you go up in levels, they represent some like their children. So like this one has children of these two. And so like the total size of this is 4 because it combines these two. And, you know, same for this, like 3 is 2 plus 1 and such. And then this one combines these cells. And then what this structure will let you do, it will let you do operations on ranges and then be able to stop early. So I'm going to explain what I mean by that. So let's say you wanted to query, or let's say you wanted to flip this range, like you wanted to flip, you know, the compressed coordinates of ID3 to the compressed coordinate of ID7. When you go into your segment tree and it goes into this cell, it will see that like, oh, the range I'm looking at from 3 to 7 completely covers this cell here. So in that case, I don't need to go further down the tree. I can just save some partial information here and save myself from the work of actually going to every single node underneath me. And in this case, I have what you would need to keep track of, the size, which is what I have here. And then the flip bit, which is, I have it at like lazy. This is like for, this means like lazy propagation. So if something has like a flip bit on, if you don't go to the children immediately, like they may not have like, you know, the correct amount of flip bits because they haven't been flipped yet. But as long as you, you know, propagate that flip bit down before you check the node's children, then, you know, everything will be correct. It saves you computation. Like it doesn't work without this kind of lazy propagation concept. And then also to complete the query, because it was from 3 to 7, like when you get, it actually happened at this node first, that you see that like it doesn't completely encompass it. So let's like consider the children. And then 7 would do the same kind of thing here. Maybe I should like bold these. I wonder if, oh yeah, that doesn't work. So for 7, it says, oh yeah, it doesn't completely cover it. And I could go to 4 and, well, the cells with size 4 and 3. And then this one would say like, oh, there's like nothing covering this at all. So it stops. It just goes like there's, you know, nothing to flip here. And then for 3, it's like also a partial covering. So it goes to its children. And then finally it gets to these two. And this one is like, oh, there's nothing covering it. And then this one is like, oh, I completely covered. So when you have this operation where you're doing this update on a range, it becomes a log runtime because you get to break down the range into powers of 2, like the largest powers of 2 that will fit within your structure. And that would makes it, you know, not order n, but order log n instead. And then when you want to query the, you know, how many bits are flipped, You could actually do this on a range as well, but for this problem, it just happens to be that the range is everything every single time. But you would go through and you would, count the current amount of bits flipped. When you're flipping bits, if you know the size of the range, then you know that when you're flipping it, like you get all of those bits as flipped. And then later on, if you have like partial solutions, like you know that like this has like some of it's flipped, like maybe this one is flipped and this one isn't. And then you want to check how many bits are in this when you flip it. What you can do is just do this operation. You just invert the number of bits, like you know how many there are. All the ones that are flipped become not flipped. All the ones that are, and then the inverse of that as well. I forgot which one I said first. And then this will also follow that same kind of pattern where you get to stop early at the large nodes, and that lets it be log n, and then you can finally do this in time without having me n squared, but instead n log n. All right, so any questions about rectangles? All right, so I'm gonna go back. I'm gonna be skimming through a lot of the smaller problems. Let's see, exam. Right, for this one, the trick was just finding out, like you only care about like whether it matches or not. And there's also kind of a like slightly tricky logic with like how many get the correct and how many are matching, and if you have more matches than there are correct and such. Does anyone want more details for this question, or can I just skip over it? Okay, I'll be moving on.
That's good.
Thanks. All right, so goat rope. So this question, you have a fence post that is going to restrain a goat, and the post is just at an X and Y location, and then you also have a house which is represented by a rectangle, and you want to know like what is the closest point on the closest point from the post to the house, or the closest distance from the post to the house, I should say. And the trick to this problem is first you want to check the corners of the house to see if those are possible closest points. And then the other case, maybe I can draw this one quickly. Yeah, let's say you just draw some house here, and you could have like, I'll just draw like a small circle of sorts for the post. All right, whatever. So if you have it in a position like this, where it's like it's like past the leftmost side, or like the minimum X side, it's also past like the minimum Y of the house, that it would be a corner. But it could be in this position like this, or instead of being a corner, it's a point on the border of the house. And you can check for this case by checking to see, is the points within like the range of the X and Y like coordinates. Like if this point is within the X range of the house, like this, you could check just the straight line drop. Oh, it's not gonna make it be a straight line. Rip. But well, I guess it's fine now. You see that like this, the post is in the x range of the rectangle. You just can do the difference of the y coordinates and define the length of this line segment, or which would be the shortest distance. And then you could do that similarly, like if you're if it's within the y coordinate range, you can check these. And you can check them like regardless of whether they're known to be the closest. Like you could check the corners, and then also do this as long as it's within the ranges, and then that would be sufficient. Just take the minimum of all of them. All right, any questions for goat ropes? And also, when I first saw this problem, I got reminded there's like I think in the division 1 version of the set, there's this problem goat ropes, and that problem is like just like way more difficult than this one. Uses simplex. So I was like worried when I saw the set at first that I would need to go into that. All right, repeating goldbacks. So for this one, you're giving a number, and you want to do this like operation where you find the pair of primes that have the largest difference that sum to the number, and then that difference becomes the next number in the series, and you want to repeat that operation until x is 2 or 0. So some observation for this is that the more primes that you have to check, because you would start with the smallest primes because you're looking for the largest difference. So if you have like a number, let's say, where you check like the prime 3, and you check if x minus 3 is a prime, and it is, like that would be like the largest difference possible. Although in this case, like in this problem, like 2 is also a possible number, even though 2 is the only even prime, and all the other primes are odd. So if you take the difference of an even and an odd, you get an odd number, but you just want to look for even ones. But the edge case is just if you take 2 twice, then you can have 2. so for 4, you can take 2 twice. But besides that, no other case will use 2 as one of the primes. It would always be 3 or one of the larger primes. But yeah, you can check the smallest primes to get the primes that are furthest apart, and then as you check larger and larger primes, the difference between the primes is getting smaller and smaller. And once you find the next once you find a match where like yes, these pair of numbers are primes, then that becomes a new number, and you repeat the process. And because when you're searching for the next number in the sequence, the larger you search, like the smaller the difference becomes. But then the smaller the difference is when you find it, means that the next number in the sequence is going to be smaller, and the search for that number is going to be less than that for it would be for a larger number. So you can just keep repeating this process and not have to worry about running into time limit issues with x being just a million. All right, any questions about this problem? All right, moving on. Illiteracy, I kind of explain this when we're talking about like any of the problems, graph problems. So I'll just skim over this quickly here. You have like a starting string of 8 icons. They can be A through F. And each of these letters has an associated operation with it. And every step, you pick one of these icons and you do its operation. And then you get a new string based on what the operation did. And then you can repeat this until you reach the target string. But you have to pick which operation to do, which is why this was a BFS. And you want to find the smallest number of steps, which is why this is a BFS instead of a DFS. It's just easier to get the smallest number of steps with a BFS. And when you're saving your state, you can save the state as just whatever the string is, and then there are 6 to the 8 possible combinations, which is enough time to visit every state. Any questions about illiteracy? All right, moving on. So we talked about rectangles. Knockout was in between. So with this question, you have a starting string of digits. And what you're doing in this knockout game is you are rolling some dice, and then you remove dice, or you remove numbers from your sequence that sum up to whatever the dice summed up to. And then you repeat this until you can no longer remove out any such subset of numbers, and then the game ends, and then your score becomes just whatever digits you have left. So for example, in this case, you roll a 1 and 1, so you rolled a 2 combined. You have 1, 3, 4, 5 left, but there is no way of taking out digits that sum to 2 because 2 is gone, and there's you can't take like 1 twice. You can only take the numbers like a single amount of time. So there's nothing that you can do here. So the game ends. In this case, you print like -1 for the numbers you take because there's no possible set, and then your score is just this number basically, where you just read it as as if it were a base 10 number. And in this example, it actually is possible. Like you roll a 1 and a 3 here, so you roll a 4 combined. In this case, the way to get the minimum score is to take 1 and 3, and then this is like the expected score is like 151. And to get the maximum, you can just take the 4 because it sums up to 4, and yeah, that leads to the maximum score. They do give you this this hint that is impossible for 2 different combinations of digits to yield the same expected score. This is useful because if there is multiple possible solutions, it would be like unclear which one to print out, but they just guarantee there's like, no, there'll never be multiple solutions. So if you find an optimal answer, it's you don't have to worry about other ones. So with this problem, one thing that kind of pops out is that the number of digits that you given here is very small. It's like there's only nine of them. So this means that you can do a bit mass DP for this. And then before I get into that, there is another solution that doesn't use a bitmass DP. It just like kind of searches out into DFS to find them, which I think is possible because just like the kind of like small number of overlap between states when you're removing things. But let's talk about how the transition will work. So if you're doing a bitmass DP, the state or like, the bitmask would be the state, and that would represent, what numbers are left. So like in, actually here, I think I have, an example here. So let's say like you just like just think of like, this is like what this place represents, and you can have a, a binary number to represent something here. So with every one here means that this number is still present. So you can see that 1 and 2 are still present, and then 4 and 5 are still present, and then 7 is present. So let me just write that down real quick. So it would be like 1, 2, 4, 5, 7, just like that. Because with the question is always increasing. So if you fail to meet like a sum here, like this would be your score. You would just take this number. But here, that's not what happens. Let's say like you rolled a 7, in which case you can transition in a few ways. But in this case, I was like, I threw out this possibility. Like you'd say you take the 2 and the 5 to add up to 7. And then how the bitmask transition would work is that you would just look at the, you would flip the bits for the 2 and 5 positions. Like this would be your new state here. And just again, like there are only 2 to the 9 possible states, for a binary string of size 9, which is 512, which is, quite reasonable. For the transition, there can be like multiple ways of taking a certain number, but there also can be like multiple possibilities for what you roll in the dice. One thing that's nice about the bitmask DP is that the bounds are pretty small with what your state is, so it lets you kind of avoid pre-comp that is possible to save on time. But if you just have like, let's see, 2 to the 9, say times, right? So you have all your states. It says 2 to the 9, and then when you're looking at the dice, what you can do is just kind of actually just do 2 for loops and just leave it at that. You could pre-compute like the probabilities of every scenario, but you could also just do that inside your DP because you can. So 36 possible of those, and then you want to take out like a bitmask that like sums up to whatever the dice summed up to. And there are only going to be like a few ways of doing that. Like maybe at most 20 or something in that range. But you would need to find those ahead of time. But it just so happens that you could just consider all of them and you're fine. Just look at every single one because you can. And this is just 512 times 512 times 36. I guess I can just do that here. To prove my point. Yeah, just like it's under 10 million. If you do the other solution where you don't save your states, I think you do need to do like all the pre-comp that you can to get it to work. Because that one doesn't optimize out. Like you could visit the same state multiple times. But yeah, it is still possible to do it that way. Any questions about knockout? All right, moving on. see, we talked about this one. Random index vectors. So this, I'm just gonna skim over this problem. It's kind of implementation heavy. You have a representation, like two vectors, and the input in their compressed format. And the compressed format depends on like the indices of the active bits in the vector, and the bits in the vector could be 0, 1, or -1. And the way that the compressed representation works is that it's first is how many bits are present, and then that number of bits follow, and the bit is represented by its index, and then if it's negative, it's represented by its negative index. And your operations are addition, multiplication, rotation. But what they're asking for is just for you to do all the possible operations. Like you want to print out the sum of them, print out the product of them, rotate the first one, rotate the second one. So you just go and do all of those, and you follow their instructions. With a rotation, it rotates in a way of subtracting and then loops around. So like in this example here, you see that there's there's a bit in index 18 here and one in 22, and they say k is 13. So you do, okay, I'm going to rotate 13. So this 18 becomes 18 minus 13, which is 5. And then 22 becomes 22 minus 13, which is 9. And then, for the first couple of numbers, I think it loops around and such. So you have to keep track of the maximum size is this for that to work. Okay, any questions about random index vectors? Okay, moving on. All right, area rug. So this one's a more challenging problem. So they give you this this whole map or grid of clean or dirty cells, I guess spots on the floor. And you have a size mat, which is a square. And you want to know for every possible count of dirty spots that can be covered, how many ways are there to do that? So what this sample input means is that there are 16 ways of covering 0 dirty squares, which are the solutions that have to do with putting the size 5 mat within these clean cells. And then for getting 5 dirty cells, there's 16. This would be if you're placing it so that one of the edges is covered, and then there's nothing else on the edge. And then there's also the case where there's 9 dirty cells covered, and these are the 4 corners where you get the 9 dirty cells like this by putting it in one of the corners. So the problem has its catch comes from the input size. Input size. So the grid can be up to 1,000. So you can do 1,000 squared, but then the size of the rug can go up to 100. So if you try to just consider, every single placement, and then also counting them, it gets to be too much. You can't do n squared times s squared, because n squared times s is already 100 million. So that's kind of the cap of what you can do is n squared times s. And there are a couple of ways of doing this, and they both deal with kind of pre-computing like ranges of cells and like how many dirty spots there are in them. Let's see, do I have, yeah, here it is. This example. So there's a way, like a pre-computation that is useful here, which is, I'm calling it like sum, like row column. And this represents how many dirty cells there are, for the rectangle, just starting from, the first position. So let's say if you're looking at position 3, 2 here, you would look at all of these cells. And you could go like, oh, there's like 1, 2, 3, 4, 5 dirty cells here. So this value would be 5. But the kind of the helpful part of this is that you can build up your answers from previous answers. So let's say that like hypothetically, you're going row first, and then like, you're going, first you do column 0, and then you go like row across and such. That means that you would have like the sum values for the previous locations. And yeah, hi, Jacob. Sorry, if you're considering this this rectangle, what you can do is go like, okay, I know how many there are in this position, and then I can also count how many there are from this position, because this one is like, it's before it in the row. You would have just calculated this. Say that like this is blue, but you may have noticed that like, this was counted twice here. Let's just make this green. But what we can do is we're like, oh wait, this is another rectangle with its corner at 0, 0. So you could do, here, let me make another text box for this. So you want to compute it using the previous values. You could go to like, the previous row, if it is there. That's the value from the previous column, like this. And then you can subtract out the double count, like this. And then there is one last piece, is that this cell could be dirty itself, say. So in that case, you just you add 1 if to this sum if this cell that you're looking at happens to be dirty. And that lets you, build off your previous answers and get this like array populated for, all the cells in the grid. And then when you want to calculate, how many dirty cells are in a certain rectangle, let's like reset this. Let's say we're going to look at maybe like this section. This section. Let's say we're saying like S is 3 here in this n equals 5 grid, and we want to consider this section here. What we could do is we could take all of this first, and then subtract out this other position. I'm gonna have more colors, aren't I? Right, so we added in this, we're taking out this. We're still looking at this, so this is also too much. So we're gonna subtract out this one going up. Let's just say this was red, not the outline. And then there was this overlap again. But this time it's we subtracted out this section twice. So what we need to do is add it back in. This is, inclusion, exclusion. So you would look at this cell and we would add this one back in. So we do this position minus this, plus this. And you could do that to find how many dirty cells there are in any particular, S by S position of, or any rug position on the floor. And with just checking your sum array a couple times.
So how would you implement the inclusion exclusion with the summary? Could you write that down?
So do you mean more than oh, actually, yeah, I see what you mean.
Because because the summary, it stores the mats based on their corners, right? So won't there be like a ton of spots, like for example, when you're getting the blue section, like your corner would it be 0, 0 or 0, 1? Like, oh, okay.
All right, so let's do it again like this. So we have RC is the like this position here, like this corner. So we're going to sum from this position first, and then we're going to take out the sides. So it's going to be minus this, and we're going to go like R minus S for this one, where S is the the size of the rug, and then we're also subtracting this one, which is the same row but column minus S, and then we're going to add back in the last portion here. And then you have to like loop over, all the valid positions of R and C, and then you have to, watch out for, this being like, negative. I guess if you're looking at the propositions, you don't have to actually worry about that. But does that answer your question?
A little bit. So, okay, how do you know that like when you're doing the like beforehand, sometimes you wouldn't actually have to add sums. So wouldn't you have like an if statement checking to see if you can actually add that pink section, because sometimes there isn't a pink section to add. Like if you're calculating the
right.
blue.
So let's say if let's make this clear, and say we're looking at maybe like this section, for example. Like we would we're still adding this in, but when you tried to look at this, like this cell doesn't exist.
Yeah.
So you just say, okay, like this is 0 instead. And this one exists in this case. So we would subtract that, but then this one like doesn't exist either. So it's again 0.
Okay, so for each sum coordinate, or as like for each sum sort of like spot and the 2D array, it's based on the bottom right coordinate of a rectangle at that position.
Right, it's like you have a rectangle that goes from 0, 0 all the way to its bottom right corner at whatever row column is we're talking about.
So you'd pre-compute all that.
Yes, you pre-compute the sum array using your previous answers like this. And again, if this doesn't exist, it's 0. and you could get this array populated for, every single position on the floor. And then you would loop through all the possible rug positions, but just as like a double for loop. And then you would do this. And like I said, if it doesn't exist, it's 0.
And then just one more question. When you are doing the pre-computing, and so like just for an example, if the sum array, like for the blue section in the on the diagram, at row 2 column 0, so okay, I think I see it now. So like if it was like row 2 column 1, you would color in that one column with blue as well. Like assuming you're just accessing value row 2 column 1, that would be the blue to its left.
So
and
wait, row 2 column 1. Oh, this one.
Yeah, and then so that would be up, like it would take up the blue section and that line as well. It's
Like if you did this one?
yeah.
Yeah, it would be a mix of these two colors.
Okay. I see it. Okay.
All right. Any other questions on rug? All right, let's see. What do you have left? All right, sculpture. This problem is pretty straightforward. You wanted to count the number of locations, or rather display them, locations that have, that are surrounded by higher cells. And, these are the ones that need a drain because they're going to get filled with water when it rains. So you just, read in this, and you have to look up, above and below you and left and right of you. If every one of those cells is larger than you, then that you're one of the cells that needs a drain. Any questions about sculpture? Okay. Time limits. This one's also fairly straightforward, but there's kind of a little bit of a nuance at least. So you have this problem and you have judge solutions for it, and they give you all of the times for the judges to solve the problem, and you want to know like what should be the time limit used in the contest, given that the time limit has to be an integral number of seconds. And for the judge solutions, all that really matters is the largest one, because that's specified in the problem. And you want it to be like this number times this at least. So in this case, we have like 5 times 250 is what we wanted to look at. And that's, 1.25 seconds. But because we need it to be more than that, we have to do the ceiling of that, and that leads us to 2. And well, yeah, this is in milliseconds, and your output is in seconds. And that's pretty much the gist of this problem. Any comments on that one? All right, then to tell the truth. In this problem, you have a set of people, and you have this, each of them have a claim that is talking about how many of them are liars or truth tellers. So if you look at this case here, the first person is like, there's exactly 1 liar. And the second person is like, there's either 2 or 3 liars. And the third person is like, there's exactly 2 liars. And you want to know, what is the largest possible number of truth tellers? So in this case, with 2, you could say 2 people are telling the truth. And it would be here, the second and third speakers, because 2 is between 2 and 3, and 2 is between 2 and 2, and then this one does not fit 2. So there are exactly 2 people telling the truth, and that fits. And you can't have more than that. Like if you tried to say 3, like these 2 would be lying, and that doesn't fit. And then it's also possible that the number of statements are inconsistent. So this means that no matter how many people you think might be lying or telling the truth, when you try to like cross-check that with what people are saying, how many liars or truth sayers there are, or I just suggest say that if it conflicts with how many people are claiming are telling the truth, then it's possible that there's no solution. So a helpful kind of tip with this problem is when you're trying to think of ways of tackling this, if you're kind of reading the samples, you might also notice this, that if you start with a solution to the sample, then it's pretty easy to verify whether it's possible or not. You can just look through and go like, oh yeah, this one and this one match, and then that's also 2. So then like that works. It just so happens that is pretty much the approach for this problem. You start with the potential answers, and then you just loop through and check and see if it works. And if it does, then you have an answer. If you're looking for the largest possible number of truth tellers, you can just start with saying, they're all telling the truth, and then try that, and then like, oh, that didn't work. All right, well, like maybe all of them minus 1 is telling the truth, and then you check that, and then like, oh, maybe that worked, and then that would be your answer. The first one going in descending order. I think this problem can also be kind of misleading if you don't get that observation. It looks like you have like all of these ranges. You think I can find like the intersections of all these ranges and see the largest like overlap, and then try to like cross-check that with this and that, which I think there are probably solutions like that, but it's just way overcomplicating the problem. So any questions about to tell the truth or any other problem? I can like go back to some other problems.
I'm a little bit confused on how you check to see if a truth number is valid. Like, so basically, is it just let's say for like the first example, if you're checking if all 3 were telling the truth, how do you know it's not all 3?
Right, so you would say, okay, like, propose that there are 3 truth tellers. So now you look at the first person, and then he says there's exactly 1 truth teller. Well, what, like, 1 truth teller is not 3, so he has to be lying. And then you look at the next person, and they say, no, it's between 2 and 3 truth tellers. And then like, okay, so 3 is still a possibility. So this one would be telling the truth. And then you look at this one, and then, 3 doesn't fit into just 2. So you've looked at, all the responses here. This guy lied, this guy lied, this guy tell the truth. Yeah, you found only 1 person tell the truth, but that's a contradiction because we proposed that 3 people were telling the truth.
All right.
Let's see. For the people that join later, I will be posting the recording of this. So if you just wanted to talk about questions, like how to do them, but if you have like specific comments on something, I could go over that. Oh, let's see, there's someone in chat. So Kyle's heading out.
I got a time limit exceeded on the gold badge problem. I was wondering like if you could, because I did the way that you said, like you check the lowest and the highest and just keep getting like closer and closer towards the middle until you get something that matches. But I got time limit exceeded, so I don't really know what to do.
That probably has to do with the way you're handling finding primes. Are you using a tree set to find the primes? Or are you just using an array?
I was using an array list, I believe.
Yeah, so an array list, when you try and look up an element, it's n, meaning it'll look through all the elements up to the element you're looking for. So if like you have 20 and you're trying to find the next prime number that's smaller than 20, it's gonna loop through all the prime numbers smaller than 20 to get to that number. And that's gonna be too slow once the numbers get to like 10 to the 6th. So you need to make what's called just a tree set. Just literally make that array list into a tree set. And then you do what's called flooring. You do like set.floor, and it's just a much faster way of finding the next greatest prime number that's smaller than the given number. You can look that up in more detail, but basically just a tree set and use flooring to find the next prime number, and that'll probably fix that.
Okay, thank you.
Yep.
I could also take a quick look to see if that was along the right track. All right, let's see. I guess I should show this. Sorry if you didn't want me to do this on the stream. Prime under X. Okay, I see you're checking if a number is prime like this. And let me see, you get all the primes under. Oh, this is just, you're getting all of them, right? This is an array list. Gotcha. And then you just check, if it's prime or not. Yeah, I think that the problem here is this portion. Because X is like up to like a million. And when you do this is like really close to like a million squared.
Well, that's just creating the sieve though, right?
Isn't
Like,
it?
yeah, it's just creating the sieve up to
Is
X.
is she committing by? Oh, wait, maybe I'm not reading this quite right.
That's just me
So-
like making an array.
Yeah, I was just seeing like you're
all
not
of the-
doing any squared checks. Okay, but you have the
It's just an array list of the prime numbers.
primes here.
Yeah, I think you like if you're gonna do this.
Yeah,
you-
you're checking all of the numbers less than a number and checking to see if it's divisible by any of those. An optimization for this could be like you start at the square root of the number and go down. But I think that doesn't work either because that's kind of like a million times the square root of a million, which is 1,000, which is a billion, which is kind of close. But I think they're like resources for like doing prime sieves in here. Actually, I can show mine.
Yeah, that one looks like n squared, right? And then sieve is supposed to be like log n log n,
Yeah, like
where you
head
have like
login? Yeah,
some
I think it is.
some like n log n, something like that.
All right, so I'm gonna share my IDE here.
Yeah, they're
For
your
this problem.
doing the square root of n. So it's just a little bit faster, and that's what helped me solve the problem. Because I was also getting time limit exceeded until I did
Yeah.
that.
It's like the tricks for this prime sieve is that when you're checking for a number as prime, like first of all, you can well, this isn't exactly the same as like checking at the square root of the number, but once you find like a number as prime, what this is doing is like you've already checked for all of the smaller primes, so the largest prime that you can make with that you haven't considered before is just like the prime squared, and you're like looping through and you're marking off things as being not prime by looking at all the multiples of a prime that you found. And you know, with this kind of trick where you're incrementing by the prime each time instead of by one, and this like is also kind of like a smaller optimization for it, but with that together, it's I think it is n log n to do this, or I forgot it like it might not be exactly that, but I think like you can treat it as such. The runtime calculation with this was not something that I remember right now. But yeah, with when you want to do, you know, getting a lot of primes, usually the best approach is to make a prime sieve, you know, knock out everything that's not prime in your prime sieve, and then just take out all the primes afterwards. All right. Any other questions about stuff?
I'm good. Thank you for today. I'm gonna head out.
All
Yeah,
right.
thank you.
Cool. Thanks for coming, everyone.
Thank you. Bye
All
bye.
right. Bye. Closing it off.